start recording our term project deliverable video now. And my name is Liao Kuo-Yu, and my GitHub name is KYL6092, and my partner is Yi-Chiuan. RYANYCS is his GitHub name. And at this time, I want to thanks my partner Yi-Chiuan to help me collaborate for this term project, AES Pipeline AES-GCM Accelerator. This report is to optimize the ACE standardized in um, FIPS 197 and published in 2001 November 26, and its functionality is to encrypt and decrypt plain text and confidential data in our daily application, daily life. So it is important to concentrate on its performance because the ACE is iterative and so many times. For example, ACE 128 is for 10 rounds and 256 has 14 rounds. If we want to gain the performance of the ACE, we need to do some parallel or pipeline. And since the functionality of the ACE is the round based, so we need to uh, develop a pipeline accelerator for streaming data and stream out the cipher. And now I want to introduce our acknowledgement for clarity. So it's your turn, Yi-Chiuan. Let's talk about our collaboration.
Okay. Hello, my name is Yi-Chiuan. And before start, I also need to thank my partner Kuo-Yu. He, he helped me to test my AES design and integrate this AES design into the Jserv and the Jserv sim, make it run in the Jserv. Okay. So first, for our contribution, before we start to develop our high performance pipeline AES accelerator, we need to read in the AES and AES GCM standard. So I first reading the list standard, and before I start to design our personal high performance accelerator, I first using software to implement the AES and AES GCM to make sure that I am already know the all underlying technology of this standard. And second, after I make sure complete the software implementation, I try to implement the standard AES core by system Verilog. And this AES core is the pipeline version compared to the baseline AES core. It can increase the throughput very, very large, yes. And after we finish the AES core, after that I complete the key expansion, and before that I complete the AES CTR mode and implement the component of the AES GCM need. So finally, I complete the AES GCM accelerator by pipeline AES CTR and an iterated GH module. So after that, my partner Kuo-Yu is helping to integrate that all system I designed to test in the Jserv environment. And it's turn to Kuo-Yu to introduce his contribution.
Okay, let me do some supplementary for each change, and because the development of a hardware accelerator is a very heavy, I think, heavy works for designer, and because we have some different schedule for learning, because maybe doing something else or Yi-Chiuan is doing something else. So we have collaboration like this. Yi-Chiuan will develop the AES core, AES-CTR, and AES-GCM at the beginning. But if we want to integrate them with the system, such as RISC-V or the Rocket core, we need to make sure everything will be done in an open source environment, such as ChipYard. And here we have a ChipYard environment at the beginning. I encounter some issues, and these issues will be introduced later. And next, because we want our materials be open source for everyone, so we don't use the EDA tools such as Synopsys, Design Compiler, Synopsys, VCS. We choose the Chisel test for our simulation. But Chisel test is an older version of the ChipYard framework, so I spent some time on checking the log and change log. So finally, I choose the Chisel sim and black box some implementation for the simulation. And here we can see each one have done the pipeline AES core. And next week, for example, next week I need to integrate his implementation with our ChipYard black box integration, and so on. If each one done a key expansion, I need to integrate his module into the black box implementation. And if each one done AES CTR, and then I need to generate a test case such as one kilobit or 1 megabit data for testing his work. And for now, I think this collaboration is very fluent because we have some works, but we have to do the high performance accelerator in the end. And now we want to switch to the issues I encountered in ChipYard environment. So because an instructor remind us to rebuild some baseline iterative ACE design, and we encounter the version conflicts, and this is very annoying. So in the end, I chose the latest ChipYard version for our project. And if you take a look at our notes, you will find a very clear and fresh setup instruction for you to reproduce our AES high performance implementation. And next, I want to let Yi-Chiuan introduce his implementation or the issues he encountered. Okay, it's your turn.
Thanks for your introduction. It's time to let me show my introduction, my issue when I'm developing this AES-GCM Accelerator. When we develop the AES-GCM Accelerator, we conquer one problem. One problem is that, let me see, if we want to implement the GH function, because GH function is a multiplier of the finite field number, and this finite field is very large. It has 128 bits. So if we implement this multiplier directly, we will, of course, this multiplier is the critical path of the full circuit. So to reduce the computational complexity, we use an algorithm which named Karasuba. This algorithm is use the art of the divide and conquer. It divides a large number of two-number multiplication into fewer smaller ones a number to multiply and add them together. We can see here as the example. If we have two numbers x1 and x2 with the bit length 128 bits, we first, if we directly multiply this number directly, and this will be very expensive for our circuit. So we can split this number into the smaller one. And the smaller one, we can use some substitution to result a smaller number multiplication. Okay, so this is the Karasuba algorithm. And before our intro, after our implement this multiplier, and finally I complete the ghash function, I encounter another problem. This problem is that I design my module like AES-CTR and AES-GHash function. We need a handshake mechanism to make sure these two modules send their data correctly. So I use a FIFO to become a bridge to these two modules. But when a FIFO is not fall in this cycle, but maybe it will fall as the next cycle. And but the top module will send its data into the downstream module, and it will, as when this cycle the FIFO was full, and finally they will miss the data. Yes,
Okay.
they will miss the data. So we use an signal that mean have full or almost full signal in the FIFO to notice that, oh, hello, my FIFO is ready to fall, so you need to slow down your mass data sending. Okay, so this is my issue when integrate this system. Okay,
I
so
I want to make some supplementary for Yi-Chiuan's description about uh, the FIFO in GH, and this can be seen in our notes because I also want to show the issue. So, Yi-Chiuan, can you help me scroll down the page to the experimental result in ACE? Oh, not there. Okay, yeah, and yeah, okay. No. This FIFO and next the third, yes, here I try to use the ASCII flow to describe the issue, because if we have the input too quickly in our system, like here we will have a look at, yeah, A B C D, right? This is the quicker and faster data input. But if we have the slower operation or the Kalazuba calculation, our A and B will not align to the input. And now if we have the B output one to the B input, and C, it cannot find the B because the B is overrated. So this is the issue that Yi-Chiuan's encountered, and we have some trade-off because this is the hard problem for not knowing the input size of the data. So we inevitably to reduce our calculation cycle. That is increase the critical path. Yeah. So after this, I want to justify our experimental results, and we utilize the YOSIS HQ to evaluate our gate count, but we don't have the foundry data. such as TSMC, UMC, this process data. So we only have to use the open source, that is the estimate the NAND counts for our area. Now we have a look at if we have ACE ECB table about table 4 ECB, we will find that the gate count will be 32,000. Oh, this is big. And the baseline code is an Yi-Chiuan, can you help me to switch the experimental result? Yeah. This is the baseline code of the instructor providing. And here we have 2,000 only. But if we have a pipeline design, all hardware resource will be duplicated. So if you have a calculator, try to estimate, you will find the hardware resource is 12 times. Yeah, this is because we have the AES 256, and 256 have a key length and different key lengths and a different number of rounds, and the number of rounds is 14. But we have tried to reduce the cost, so the times is not 14, it's 12. Yeah, we have some contribution. And now, if we take a look at ECB, CTR, the gate counts, we will find that the area cost is 33,000, and compared to the ECB, it's more than 1,000. 10,000. Okay, I mistake the 1,000 is for 30 and 10,000 is 40. So our gate count is 300,000, right? So just a mistakes. So 10,000 increment for CTR compared to ECB. This is about the FIFO implementation, just like our notes and describe. And now let's take a look at GCM. GCM is 52,000, and then compared to the CTR is more than about 20,000. And this is makes sense because the Karazupa multiplier is used in our pipeline design. And now let's look at cycle counts. We will find that the baseline code. Yi-Chiuan, can you help me switch to the baseline code of the experimental result? So we have found that ACE 128, it needs 84. And when the encryption of the many blocks, it will increase to the 5,000. If we have 1 megabytes, yeah, and let me check the digit. 1, 2, 3, and 5,000, 5 billion, right? 5 billion cycle counts. Billion, okay. Million. Sorry, it's for tired for me. Million. And let's look at our high performance ACE experimental result. Yeah, everything is half, roughly. So we can check that, and yeah, this is a promising result for future integration with system. Okay, and let's check about the time. It's not remaining for remaining about 10 minutes. So let's move on to the next phase, the demonstration. Okay. The demonstration is let Yi-Chiuan introduce his code.
Okay, this is my repository. My repository is to implement the AES-CTR and AES-GCM module. And this implementation is using system Verilog language. So let's look at this repository structure. we have a source directory and a testing directory, and one including directory. This include directory is used to store the configuration, like the key size. If we design different key size, then when we synthesis or simulation the Verilog code, it will set this key size to the module. Okay, and let's go back to the top directory. Okay, and the source directory contains my software implementation and the RTL code implementation. Okay, and the RTL code implementation has several modules. This module have like the AES. AES is the core module. It is the it is used to increase the plain text and output the ciphertext. And here are some other wrapper like the AES-CTR. AES-CTR is a operation mode of operation of the AES. So it will input an initial vector and the key. It will using key expansion module to calculate the run key and then setting the initial counter. After all thing is done, it will set the DIN rated to high, and then the top module can keep sending its data into this module and increase the data. Okay, this is an example of our RTL code. And because I am my response is to design the system. So each time I finish implement a module, I will write in the test. I will write in the test bank to make sure my implementation is has passed the test case.
That's a good
So
habit.
yes, so there under the test directory there are many tests to which each test has a test bench file and test case. Okay, so if we want to make confine one module, we can run this test, and it's time to give the demo. First, we can clone this repository.
And remember that our operating system we use here is Ubuntu 24.
Yes. Okay.
Just remember install your GitHub Git
Okay.
package.
Okay. Like this. Now I'm cloning this repository, and we use ls. We can see all file is here, and here we can see that here is a make file. Make file. This make file contain all target that we can do. For we can take this file first. We can see here as a vsim or VCS. Vsim indicate the model sim, a model sim simulator. It is a free for community use simulation. So before we integrate our system into the Jserv sim, I will use model sim first to test our my module. Okay, so we can use max list test to show how many tests we can use and how what target we can build. So if I want to build and test the AES code, we can use Mac. Before running this Mac, we need to make sure to make a directory called output, because all web dump will dump into this directory. And before we using model sim, we need to create a working directory. This working directory may have a executable name vlib. Vlib.x. We can use vlib.x and work to make the work directory name work. Okay, so now we can make the text. For example, I want to test the AES. We use test AES, and we want to choose model sim as our simulator. So I use that the sim, and then we can determine the key length. We can use this keyword. For example, I want to use 128 as bit as my key size, and use this command. It will run the test. If the test is success, we can see the choose case here and as the simulation pass message. Okay. And if we want to test the 20, 256 key length, we can change the key length parameter here and enter. If we set a key length, we will show the info message says that which key we currently use. Okay. And if the simulation pass, you will also see the simulation pass message here. So this is my repository usage. And now I bring its turn to Kuo-Yu, my partner Kuo-Yu, to introduce his repository.
Oh, okay. Thanks Yi-Chiuan for introducing his code, and now it's my turn to introduce my Scala or Chisel or Verilog. Yeah, three codes, but Chisel is written by Scala. So this repo is maintained by me to integrate our hardware accelerator in system. For example, Rocket Core, but this time we have no more time to do this. And now we have looked at this repo, and this can be found in our notes also. Okay, now let's take a look at this SBT. This is very important file because Chipyard is platform for you to integrate your accelerator and other existing projects such as Rocky Core. So if we want to simulate this Rocky AES-GCM report, you need to fresh set up first. So let's take a look. Let's take a look at the fresh setup. And first, you need to clone the chipyard repo, and this will be a lot, a little of your time to download this. And next, you need to check out to the tag for this 1.13.0. This is the environment we use this time. And next, to ensure your Java is installed and everything is fine, you need to build this build setup dot shell and riskify tools. This -s is to skip some package we don't use this time, such as FireSim or FireMarshal and Search CT. And next, you need to source the environment shell after you build the riskify tools, and this will switch your workspace to the specific virtual environment. And now you need to change your directory to the generators under the chipyard and add the Rocky Ace GCM repository. And some workaround you need to check is the chisel version and some dependency, and I will leave this to you. So next, I want to demo AES-GCM, and let's to uh, okay. Oh, okay, it's recording. So if you have done your chipyard installation and makes everything right, you need to source environment shell file, and this will be like this, and you will find that your prompt, the prefix of your prompt is noted like this, and this is my host, so it will change in your machine. And next, you need to follow the instruction in notes and change the SBT build SBT file. And next, you can type the comment. And because the comment is so complex, so I have a make file for this. This is a rule I define. So if we want to test the AES-256 GCM, you can do it by this. Wait a minute. Just look at the make file. Okay. So I provide some rule here. The main command is SBT and switch the project to the Rocky AES-GCM and test the specific function. And for this demo, I will test the GCM in Cypher and dump the VCD file for justification. And before that, you will you will be curious about my test case, right? So let's look at this repo. This repo is constructed by 3 folder, and this folder is the synthesis. Just ignore this for now. And let's look at the source code. The source code will contain 2 folders. One is main and one is test. Main is including Verilog source and a scalar source. Scalar source will contain some file for black box integration. And for example, the GCM will add some Verilog source and define the interface of the input-output, and then wrapper using a module in Chisel. And this will help us to use the Chisel sim or Chisel test to testing. And now let's take a look at test. Test will have a resources folder and a scalar folder. The scalar folder is the test code, just like a test bench, but written in scalar. And this will be convenient in some case. For example, if you want test a big data, 1 megabyte or 1 kilobyte, this will help you to define the code, just like you're using your Python or C. And the details are skipped this time. I want to show is the resource here. We have a CTR, ECB, and GCM. And GCM, in GCM, this test case is generated by a code, also provided in our folder. And this will be done by scripts. The test case generators in scripts. This is the Python code. And here we have a makefile for all possible test case. And now I want to demo is the GCM. So okay, let's take a look at this. Make sure you have under the scripts folder and type the make AES-256 GCM. If we want to manually input, just type this. If we want to random, just like make this here. Okay, so you can specify the size here. For example, I want to encrypt 1 kilobytes here, and you will see that a success keyword here. And next, you need to update this to the scalar testing framework like this. You can see everything will be copied to the resource under GCM. Last, we will type here AES-256 GCM. But here I make sure this. Oh, okay, it's GCM, and this will run the project Rocky AES-GCM test only. We will find that here we don't have any VCD argument, so we don't have a VCD dump file. We need to switch the rule to the GCM VCD, and then we will see the VCD argument is passed. And just wait a moment, and make sure your test code is configured to correct byte, because I want to use the AES 256 and 1 kilobytes, and we need to set here advanced. Okay. Okay, you will see the cipher success and text success, and how do it how did it works. So we can check the resource file here. Okay, tag is here, and next I want to check the VCD file. Just wait a moment. I need to open my file manager. Okay, so if you want to check the waveform, just go to the chip yard. Under the build, you will find the Chiso sim, and this will instantiate every test you have made. And for this time, I want to take the GCM Cipher here. Just click into the work directory validator, and you will see the trace VCD. Let's just move on to the check-in result stage. We can see that everything go here, and I want to check the tag. Okay, this is the GDK wave software. So if we want to see the result, just press your control and use your mouse, and we will find the answer here. Okay, just wait a moment. Okay, and my demonstration for framework of the RCC accelerator is done. So thanks for listening for our reports, and anything else you want to talk about, Yi-Chiuan. I just some tired. Oh, your microphone is not open.
Okay, sorry. That, and finally, we can analyze our critical path of our implementation. So let's look back to this HackMD node. So usually we may think the critical path of standard AES core may be the S bug or substitution bugs. If we implement this S bug by LUT, but if we implement the GH function by use the Galois field 2/128 multiplier without using Karasuba algorithm, this multiplier may be the critical path. Why? Because the Galois 2/128 multiplier, which may contain at least 128 logic gates in the disk. So for one database, it will have at least 128 logic gates. So this must be the critical path. After we adapting this algorithm, the multiplier width will reduce from 128 bits to 16 bits or even 8 bits. And since the multiplication in the finite field does not contain any full adder or half adder or carry bit, it's just an XOR or AND gate. So it can furthermore reduce the database for this multiplier. So if we implement the Karasuba algorithm, the critical path of the multiplier will be slow. So let's look at the S box. The substitution box, or called S box, if it is a 2 over 8, or we call 156 to 1 multiplexer. If we synthesize this multiplexer to using a standard 2 to 1 multiplexer, the resulting logic gate is at least 2 layers of multiplexer. If we're using the standard 2 to 1 multiplexer, it will bring to this result, which contribute the overall latency. Because if we're using Karasuba algorithm, the multiplier will maybe only contain a gate to XOR the result, but to the multiplexer, it will contain the AND gate, OR gate, and so on. So the S bar, of course, will be the critical path of the AES-GCM circuit. And so the future work of our plan maybe will be implements using calculation to implement the S bar, not just using the LUT. So this is maybe our next future work.
Yeah.
And the analysis is done. So I think our report maybe finished.
Yeah,
Okay.
I think this is
Okay.
enough for us because the recording time is to 40 minutes. And okay, so thanks Yi-Chiuan for his report, and we want to take this opportunity to thank the instructors um, teaching our everything in modern computer architecture. We will progress. We will continue to progress our learning. Thanks for listening.
Thanks for listening.
Okay, and this video will be uploaded to the YouTube for public assessment, and the link will be provided in this note too. Okay, bye bye.